Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to tackle the harder problem, which is to program the functions that deal with the equivalent loader loads when you have distributed loads. I still haven't programmed the check inside segment. That's something we'll do later, but for now I want to focus on those things. I hope I don't forget anything of the to-dos. If I forgot, then I need to remember that later. So with that being said, and without further ado, sit back, relax, and enjoy the show. So here we are, and we need to program this stuff. Now for the nodal concentrator, I can collapse it because we are focused now on this. Here we need to know something called the load equivalence method. This is mentioned in Daryl Logan's book. We're going to use this. The idea behind this is that the work from the equivalent nodal loads on the bar 1, 2 must equal the load of the applied load on the bar using its displacement field. That's what it means. Now the displacement field can be substituted by the shape functions. You will see me integrating a multiplication between the load function and the shape function. So that's how we can calculate the equivalent loads. So you will see the work equivalence method in action. I might not reach it today, but at least I will put the groundwork for it so that we can continue it either today or for the next time. I want to remind you, the work equivalence method deals with the multiplication of the load and its displacement field, and the displacement field equals the shape functions multiplied by the nodal displacements. I want to declare my function. So I'll go to the first time where the function is missing, which is here. Wait, those should be missing too. Why are they not missing? I think I know why. I think I blundered the naming of those things. I should have changed this. Yeah, I did not change the name. That's why it's not missing. It should be missing, by the way. I don't know why it's not missing. Let me just say here, instead of concentrated, it's trapezoidal shear. And here, this is again trapezoidal shear. That here is trapezoidal torsional moment. And this is trapezoidal moment. And that's trapezoidal moment. Yeah, that should be the case. Okay, so let's start with the easiest one, which should be the trapezoidal axial. I say it's the easiest one because the shape function of the axial load is actually not really that complicated. So I need to copy this, and I'm gonna go here. So here I will basically paste the declaration. I will say this is a function. Now there is no need for object because the object, once again I forgot to mention the object here, because the object here will be included here. Now here he wants fembar length, which I will basically call L. Interpolation input, this means W1. Interpolation output, this means W2. Okay? Fembar is fembar. Fantastic. Now, how do I do that? Let me explain this to myself. Q1 equals the integration from 0 to L for Q of x multiplied by N1 of x dx. Okay? So short term, it's integration. If you write this in Word, you will see this. Integration 0 to L Q N1 dx. Okay. Now, don't get it wrong. Q can be a function in x because it could be a trapezoid, and N1 is a function in x. Now, similarly, of course, Q2 is going to be the same, but for N2. The problem here is that Q may be a piecewise function. Why? Because this is the fembar. It starts here, fembar, and ends here. Now, I could have a load that doesn't necessarily start here. So here, no load. And then I could have a load here, and here, no load. I don't know where it starts. As a matter of fact, I do know, but what I'm saying is it's not always the full length, meaning that here I have L1 and here I have L2. So how do I integrate that, right? I must define my function, define Q piecewise, which means now my Q of x is going to equal, well, first of all, it equals Q of x equals 0, and that's the case for x less than L1, because here we have no load. Okay? Now here, I copy and paste this, and just put here something like Q equals, just to denote for the piecewise definition, just to make it mathematically elegant. Here, Q of X equals a big thing. I will say here something, and I will write what this something means later. When X is between L1 and L minus L2. This integration is true when we are here. Finally, I'm going to go for the last thing. So Q of X equals 0 for X more than L minus L2. So if you are here, then there is no load. So I need to perform a piecewise integration. That's tough. Okay, let's just, first of all, for the load here, slope multiplied by X plus intercept. Because it's a linear function, so that's the function for the load. Okay? Okay. We're still not out of the woods yet, my friends. But at least we have something. So now let me just first of all define the load function. So here, the slope of the load is going to equal W2 minus W1 over L minus L2 minus L1. So it's basically delta Y over delta X. There's a minus missing here. The intercept is basically at X equals L1, the load equals W1. So you can substitute in the equation and find the intercept. The intercept equals W1 minus L1 multiplied by the slope, if you do that. I just realized by doing this that MATLAB has symbolic math. So let me just open Sims. I think it was Sims, right? Was it Sims? I need to install symbolic math for this. Okay, so we are back. And I want to ask you, before you start, to dim your light on the screen, because I'm pretty sure that you are using dark mode or something. And the MATLAB I'm going to show doesn't have dark mode. So it might have a sudden spike in your brightness. So please dim your screen before I show you the MATLAB, okay? Now that your screen has been dimmed, I'll show you the MATLAB that I have where the symbolic math is installed indeed. Okay, so we are back. I just did some tests off screen. We want to find this, okay? Those are the loads. And in order for us to find Q1, I need to say Q1 is going to equal the integration of, let's put int for integration, of Q1 N1 plus integration of Q2 N1 plus integration of Q3 N1 with the respective integration bounds. And here, Q2 is the same, but in this case, we take N2 as its integration. Now, I'm going to use symbolic math to do it. So here, CLC, clear, and Sims, and we're going to do some symbolic stuff. We're going to declare our symbolic variables, X, L, A, which is the slope, B, which is the intercept, the length L1, the length L2, and that's it. Now here, let's define N1, which equals, according to the shape functions, it equals 1 minus X over L. This is symbolic math now. This is one of the legendary tier stuff that MATLAB can do for you. And 2, I will show what it means, equals X over L. It understands mathematics like humans do. I'll even remove the semicolon to show you that in action. Q1 equals 0, that's loaded the first thing. Q1 is a symbolic expression, Q2 is a symbolic expression, Q3 is a symbolic expression, N1 and N2 are symbolic expressions. So here Q1 is 0, Q2 equals A multiplied by X plus B, so slope plus intercept, and Q3 equals 0, okay? Now look at this. I will go find Q1, which is going to be an equation, which I should declare in the symbolic math, Q1 and Q2. Q1 equals the integration. This is symbolic integration. Q1 multiplied by N1 from 0 to L1 plus the integration of Q1 multiplied by N1, that's a mistake, it should be Q2 multiplied by N1, from L1 all the way to L minus L2, right? I think it's L minus L2, plus the integration of Q3 multiplied by N1, L minus L2 all the way to L. Okay, this is our symbolic math. I'll copy this, paste it here, and I will change this to N2. I'll push F5 and show you the magic. That's the equation, by the way, because MATLAB knows what equation is. Let me show you something cool. I can call Q1 multiplied by N2, for example, and it's 0, of course. I can call Q2 multiplied by N2, and it calculates the equation for you. He just found the equation because Q2 is an equation and and 2 is an equation, he just multiplies them together and gives you the equation like human form. So those are the equations, believe it or not. Oh, it should be Q2, by the way. Let's run it again. Those are the equations for the axial load. Those also should be the equations for the torsion because of similar assumptions. So I think we have done something amazing today. We were able to use symbolic math to our advantage by finding the symbolic equations. We basically derived the equation. Now, of course, we need to check if that works or not by benchmarking, but I just used MATLAB to derive a fully fledged equation. How cool is that? I will get back to the symbolic math thing in the next video. So now I will switch back to my main MATLAB 2024. So your eyes need to adjust for the darkness. I'm sorry about that. So there we go. And all I'm going to do here is I'll call this A, I'll call this B, because I called it A and B in my symbolic math. And I'm going to copy the equation of Q1 from the other MATLAB. I'm copying it at the moment off screen. I'll paste them here, and that's it. Mission accomplished. Let's tab it in, remove the comments, and that's Q1 and Q2 for you with all its glory. Now, fembar is an error. Why? I think because we need to fish out L, right? So L equals fembar.length. And now it should be fine. I think we're fine. This might be an error, by the way. I still haven't debugged it, but yeah, I will be using symbolic math a lot. That's pretty awesome. Symbolic math is based. Okay, so we have now this for the axial load, which means I can copy-paste this for the torsion, because the torsion and the axial have similar shape functions. Okay, so now this is called calculate nodal force from trapezoidal torsion. And nothing changes here, believe it or not. Nothing changes here, ladies and gentlemen. For now, 2 down and 2 to go. Oh, it's called torsional moment, I see. So I need to add a moment here. Let me add a moment value here. So moment, is that? I think that's it. Yeah, I think that's that. We have 2 down and 2 to go. And we're going to enjoy symbolic math in the next video again. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a symbolic math-sized shout-out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank you from the bottom of my heart, as your support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing, because it helps increase the reach of my channel. As per usual, this is a Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.